Well, boys and girls, this is lesson 10.4, and here we're talking about compound events. So a compound event is not simple, like just flipping a coin or rolling a die or spinning a spinner, but a compound event is when more than one thing is going to be happening. So it starts off with talking about sample spaces. A set of all possible outcomes for one or more events is called the sample space. You can use tables or tree diagrams to find the sample space of two or more events, okay? So the sample space for rolling a die would just be 1, 2, 3, 4, 5, and 6. Those are all possible outcomes. But it's not quite so simple when we get into compound events. For instance, choosing a pizza. You randomly want to choose a crust and a style of pizza. Why you would do that randomly, I have no idea. But let's say you were going to. Find the sample space. How many different pizzas are possible? So here's the simplistic menu over here. You have two choices of crust. Thin crust, stuffed crust. And you have 4 different styles of pizza. Hawaiian, Mexican, pepperoni, and veggie. So if you were randomly choosing a pizza, what are all of the possible outcomes? Well, they're doing a tree diagram here. They started with the crusts, thin and stuffed. And then for each of the crusts, they have all of the styles. So you could have a thin Hawaiian pizza, a thin Mexican pizza, a thin pepperoni pizza, or a thin veggie pizza. Or a stuffed Hawaiian, stuffed Mexican, stuffed pepperoni, or stuffed veggie. So there are 8 different outcomes in the sample space. There are 8 different outcomes, so there are 8 different pizzas possible. Now, the nice thing about a tree diagram is it does list out all of the possibilities. But more times than not, we don't want a big list of all the possibilities. We just want to know how many possibilities there are, because that, remember, is what goes in the denominator of our probability. How many possible outcomes there are. So let's finish up this one on your own here. It says, if the pizza shop adds a deep dish crust, find the sample space. How many pizzas are possible? Well, let's think about it. If there's 4 possibilities for thin crust and 4 possibilities for stuffed crust, if they add another kind of a crust, deep dish crust, there would be 4 more possibilities. A deep dish Hawaiian, a deep dish Mexican, a deep dish pepperoni, and a deep dish veggie. So there would be 12 total possible pizzas. And I would probably try them all. Now, going down here, another way to find the total number of possible outcomes, and this way doesn't list them all out for us, but it does tell us how many there are, is to use something called the fundamental counting principle. The fundamental counting principle makes this easy schmeezy. For instance, if we were to go back up here, here's what it says. An event M has M possible outcomes. An event N has N possible outcomes. The total number of outcomes for event M followed by event N is M times N. And just in case that doesn't make it crystal clear, let's look back at this example up here. It means instead of doing this tree diagram, we could say, well, there are 2 types of crust, so we have to choose a crust. There are 2 things that could happen. We choose a style. There are 4 things that could happen. 2 times 4 is 8. So there are 8 possible pizzas. In the on your own, it said that added another crust, then there would have been 3 times 4. And we did get 12. I like that multiplication called fundamental counting principle because it makes these quick and easy. This says find the total number of possible outcomes. So find the total number of possible outcomes from rolling a number cube and flipping a coin. And here's the first method they used. They made this nice looking table. Isn't that beautiful? And then you can see you got one head, or you rolled a 1 and you got a heads. You rolled a 2 and you got a heads. Or down here you rolled a 3 and you got a tail. So all of these possible outcomes. But you could also use the fundamental counting principle and say, there are 6 things that can happen when I spin this, and 2 things can happen when I flip this. 6 times 2 equals 12. There are 12 possible outcomes. I think that is much nicer. Now, how many different outfits can you make from the t-shirts, jeans, and shoes in the closet? And you might be thinking to yourself, hey, we're in a stay-home order in the state of Michigan. I haven't put shoes on in weeks, and I've been wearing the same clothes for 5 days in a row now. However, let's pretend that that's not happening. Use the fundamental counting principle. Identify the number of possible outcomes for each event. So let's look. First of all, how many different possibilities are there? Well, there are 1, 2, 3, 4, 5, 6, 7 shirts. There are 1, 2, 3, 4 pair of jeans. And there are 1, 2, 3 pair of shoes. So 7 times 4 equals 28, times 3 equals 84. There are 84 different outfits, assuming that we match our shoes. I know a lot of you would mismatch your shoes, which then would make this even more. But let's just say you don't mismatch your shoes. So we have 3 pair of shoes times 4 pair of pants times 7 shirts. You would get 84. There are 84 possible outfits. On your own, find the total number of possible outcomes of spinning the spinner and choosing a number 1 to 5. And you might think, what spinner are they talking about? But there's a picture of a spinner right over here. So, number 2 here. Total number of possible outcomes of spinning the spinner. Well, how many things can happen when you spin the spinner? 4. And choosing a number 1 to 5. How many of those are there? 5. 4 times 5 equals 20. There are 20 possible outcomes. For number 3, how many different outfits can you make from 4 t-shirts? So 4, 5 pair of jeans times 5, and 5 pair of shoes times 5. 4 times 5 equals 20, and 20 times 5 equals 100. There are 100 different outfits you could make with those pieces of clothing. So a compound event, which is what we've been talking about, consists of 2 or more events. As with a single event, the probability of a compound event is the ratio of the number of favorable outcomes to the number of possible outcomes. So we would use the fundamental counting principle to find the number of possible outcomes, the denominator for our probability. In example 2, if you'll remember, example 2 was rolling the number cube and flipping the coin. So in example 2, what's the probability of rolling a number greater than 4 and flipping tails? Well, first, we need to find the total number of possible outcomes, which was 6 times 2. 6 things could happen with the number cube and 2 with flipping a coin. So the denominator is going to be 12. 12 things can happen. Now we want to know what is the probability of rolling a number greater than 4 and flipping tails? So what's the probability of rolling a number greater than 4? Well, there's 5 and 6. So there's 2 out of the 6 that would satisfy that first thing. And flipping tails. Well, there's 1 out of 2 chance of flipping tails on a coin. We multiply straight across and we get 2 out of 12. 2 out of 12. So 2 out of the 12 total events would satisfy that probability. So the probability of getting a number greater than 4 and flipping tails is 2 out of 12. And we got that by multiplying each probability together. Now it says finding the probability of a compound event. You flip 3 nickels. What's the probability of flipping 2 heads and 1 tails? Well, let's think about that. We're flipping 3 different coins. 2 things can happen for the first coin, 2 things could happen for the second coin, and 2 things could happen for the third coin. So, using the fundamental counting principle, 2 times 2 is 4 times 2 is 8, we know there are 8 possible things that could happen. So for this example 5, we know the denominator will be 8. Now let's think about what could happen. If we want 2 heads and 1 tails, we could have tails, heads, heads. That's one thing. We could have heads, tails, heads. That's the second one. Or we could have heads, heads, tails. That's the third one. There are 3 of the possibilities that satisfy out of those 8. The probability would be 3 out of 8. Or we could use this tree diagram where the first coin is flipped, heads, tails. The second coin is flipped, so heads, tails, heads, tails. And then the third one, for each of these, we do a heads, tails. And we can see, here's all the possible outcomes. Heads, 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 tails, heads, tails, heads, all the way down to tails, tails, tails. And only 3 of those have 2 heads. Now we're on to the on your own. It says, in example 2, what's the probability of rolling at most a 4 and flipping heads? So remember, that was the rolling a die and flipping a coin. So number 4, and it says the probability of rolling at most a 4. So that would be a 1, a 2, a 3, or a 4. So that's 4 out of the 6 for the number cube. And flipping heads is 1 out of 2. That would give us 4 out of 12. 4 out of 12 chance, which simplifies to 1 out of 3. Number 5. In example 5, what's the probability of flipping at least 2 tails? So now that's back up here. What's the probability that we flipped at least 2 tails? Well, there's still 8 things that could happen. So for number 5, we would still have a denominator of 8. And this is at least 2 tails. Here's at least 2 tails. Here's at least 2 tails. Not at least. Here's at least 2 tails. Not. So we had 1, 2, 3, 4. 4 out of 8, which simplifies to 1 out of 2 for flipping at least 2 tails. Number 6, you roll 2 number cubes. What's the probability of rolling double 3s? So for number 6, let's take them one at a time. What's the probability that the first number cube is a 3? Well, 1 out of 6, of course. What's the probability that the second number cube is a 3? Oh, 1 out of 6, of course. So we have 1 out of 6, 1 out of 6. Multiply those together and you get 1 out of, not 12, multiply them, 36. 1 out of 36 for number 6. And in number 7, in example 1, what's the probability of choosing a stuffed crust Hawaiian pizza? Well, if you'll recall, there were 8 total pizzas, and only one of them was stuffed crust Hawaiian pizza. So for number 7, there was 1 out of the 8. And we can use their tree diagram to find that out. Or we could say, what's the probability of choosing a stuffed crust? Well, there was 1 out of 2 chance because there were 2 crusts. What's the probability of a Hawaiian pizza? 1 out of 4 chance because there were 4 types of pizzas. And we multiply those together, and what do we get? 1 out of 8. So we could use our multiplying the 2 probabilities together or using their tree diagram for number 7. Looking at a couple of the exercise problems on page 425, this just says, use the fundamental counting principle to find the total number of possible outcomes. Well, there are, for number 8, for beverages, there are 3 sizes, and there are 1, 2, 3, 4, 5, 6, 7 flavors. Now, the way to do that is really kind of look at the commas, okay? Because sometimes these have 2 words, and we don't want to just count all of the words over here, but we want to count each of the flavors. So root beer, cola, diet cola. Watch the commas, because the commas will split the things in our series. Don't count the commas, because we'll always have 1 fewer comma than we do have items. So 3 times 7, 21 total number of beverages. Over here for number 9, the MP3 player, for the memory, there's 1, 2, 3, 4. And for the color, there's 1, 2, 3, 4, 5. 4 times 5, 20 different possibilities. For the clown, the suit could have dots, stripes, or checkerboard, so there's 3 there. The wig could be 1 color or multicolor, so 2 choices here. And the talent, balloon animals, juggling, unicycle, and magic, so 4 here. So we have 3 times 2, which is 6, times 4, which is 24. So 24 different types of clowns, all scary. Over here for number 11, the meals, nachos, soup, spinach dip is one thing, salad, and fruit. So we have 5 choices for appetizers. Chicken, beef, spaghetti, and fish, 4 different entrees. And dessert, cake, cookies, ice cream, 3. So we have 5 times 4, which is 20, and 20 times 3, which is 60. 60 possible outcomes for the meal. Let's just do a couple of these from page 426. You spin the spinner and flip a coin. Find the probability of the compound event. So spinning a 1, look at the spinner. It's a 1 out of 5 chance of spinning a 1 for number 15. 1 out of 5 times flipping heads, which would be 1 out of 2. Multiply across the top and bottom, and you get 1 out of 10. For number 16, spinning an even number and flipping heads. The evens, there are 2 of them, just 2 and 4, so 2 out of 5 times flipping heads would be 1 out of 2, and you get 2 out of 10 for number 16. Number 17, spinning a number less than 3, just these 2 right here, so 2 out of 5. Spinning a number less than 3 and flipping tails, so 1 out of 2 gives us 2 out of 10. Wow, hopefully 1 out of 10, 2 out of 10, 2 out of 10. Number 18, spinning a 6 and flipping tails. There's a 0 chance of spinning a 6. So 0 out of 5 times 1 out of 2 equals 0 out of 10, which is just 0 or impossible. For number 19, not spinning a 5. So that would be 1, 2, 3, 4. These 4 out of 5. Flipping tails, 1 out of 2, would give us 4 out of 10. And finally, number 20, spinning a prime number. The prime numbers here, 1 is not prime, it's unique, but 2, 3, and 5 are all prime. So 3 out of 5. Remember, that means that the only way you can get them is to multiply 1 times itself. And then in not flipping heads, which is still 1 out of 2 because not flipping heads is the same as flipping tails. And you get 3 out of 10. Excellent. So that's how you find the probability of a compound event. Well, now you can head over and do the homework, which is page 224 in your journal for lesson 10 point, whatever this was, 10.4. Excellent.